Welcome to our second webcast in our Laser 2000 webcast series. This time it's about hyperspectral imaging for agriculture and environmental health. My name is Martin Labus. I'm technical sales engineer for optical test and measurement, where our hyperspectral imaging solutions are located within our portfolio. And my colleagues my partners from Resinon, Dr. Adam Stern and Dr. Casey Smith will give us a talk about hyperspectral imaging, especially remote sensing with hyperspectral imaging. And in the end, we will have a Q&A session where we hopefully can answer all of your questions. You can already start asking questions. If there's a need for, we will collect them and present them if they are if they are interesting for the whole audience. We'll present them in the Q&A session, and some other questions that may be interesting for particular participants will be answered maybe directly or afterwards. So if you want to ask a question, please use the chat panel within the GoToWebinar panel. Okay, so now let's start. Just one small thing about Laser 2000. We're a trading company where we have everything regarding photonics. We're mainly selling in Germany, Austria, Switzerland, as well as the Nordic countries, some Eastern European countries. And with our colleagues from the Laser 2000 SAS, we're also selling some parts of our portfolio within or nearly everything in France and some parts in Spain and Portugal. So as I told before, we have a very broad portfolio. We are selling, as the name says, a lot stuff around lasers and light sources, especially for laser material processing. And laser material processing, of course, laser safety. Whenever you buy a laser, you need to be safe when using it. Then optical test and measurement, where it comes to spectrometers and other things like beam profiling cameras. Yes, and all the accessories like optics, optomechanics, scan and motion, and especially even for hyperspectral imaging, cameras and machine vision stuff. And last but not least, fiber optics for a good connection between all over the world and in telecommunication. So let's now start with the hyperspectral imaging. So what is it, or where does it come from? When we began imaging, it was all about black and white, where you could only see shape and contrast, and that's only provided by the brightness information and the wavelength sensitivity of the detector or photo plate you had before. Then we advanced to color imaging, which is mainly adopted to the human vision. With RGB channels, you have 3 spectral data points, which allows like a rough classification of what we are seeing, like a fruit. Is it ripe or is it premature? And then when we go further, we have spectrometry, and we can also see the color defined by the wavelength. in a nearly continuous state. We have a better separation of color components. So some colors that seem to be similar can be resolved to the spectral compounds. But when you go to traditional spectroscopy, you only have one spatial point per measurement. So, and now hyperspectral imaging just combines the latest 2 points, because you will have a spatial information and the relative or the concatenated spectral information for each and every image point within the visible NIR or whatever spectrum you want to see. That leads to 3-dimensional data, which is stored in a data cube in the end. So, and that's the point where my colleague, Dr. Adam Stern, will take over and give a little bit more detail about hyperspectral imaging and about Resinon and, yeah, their images.
Well, thank you everybody for attending. I'm going to give a very brief 3-minute presentation on Resinon and hyperspectral imaging. So, as Martin said, and I'm sure many of you know, that hyperspectral imaging is the combination of spectroscopy and imaging. And this is useful because different materials have different spectral signatures, reflectance spectral signatures. These are literally textbook examples of different materials. On the right-hand side, the graph on the right is various minerals. Here are other textbook examples. On the left are different types of vegetation, and on the right graph are human-made materials with their own distinct reflectance signatures. And so when you combine spectroscopy with imaging, it's this very powerful technique of doing materials identification. We often are contrasted with multispectral imaging, and here you can see the basic difference between multispectral imaging and hyperspectral imaging. On the left is the multispectral signal created from the data on the right. Multispectral signals usually only have a handful of spectral bands. Those bands are fairly wide in spectral space, and they're often discrete and discontinuous. Whereas the hyperspectral signal is continuous and gives you a great deal much more information. So finally, 2 minutes on marketing, and then I'll hand over the presentation to my colleague, Casey Smith. So Resinon, we manufacture push broom hyperspectral cameras. We design and manufacture them here. And we then integrate them into various complete systems. There are laboratory systems on the left, outdoor system based on a tripod, and today we're going to talk about this airborne remote sensing system. Resinon is located in Montana in the USA, close to the Canadian border in the mountains, and we do everything at Resinon. We do the design and the manufacturing. We've got our software team and do the integration here, so we're fully vertically integrated. Now you can download sample data and our data analysis software from our website. If you want to see what the data looks like and play with it, there's examples of remote sensing data. And Laser 2000 is our partner in Europe, and both they and us are here to provide any sort of, if you have any questions or need any assistance, we're here to support you. So thank you very much for your time, and I will hand over the presentation to my colleague.
Great. Hello, everyone. Thanks, Adam, for the overview of Resinon and hyperspectral imaging. I am going to dive a little bit more deeply into the airborne part, the remote sensing aspect of our business. Resinon does has many different systems for many different types of applications, including laboratory systems, industrial systems, and then one part of our business, of course, is airborne or remote sensing. So let me go full screen here. My apologies. Here is a basic kit that we sell for our airborne system. This system is intended to be turnkey as much as we can, so that you get every piece of hardware and software that you need to put this on a drone or an airplane or a helicopter and collect and analyze your data. We also do occasionally offer a full drone and gimbal system with some of our partners that sell UAVs and gimbals. So that's another service that we offer. This kit here shown includes a hyperspectral imager, a data acquisition device, a GPS IMU that's used to georectify the data, that is, place the data back on the ground so you know exactly where the data was taken at. We have a downwelling irradiance sensor that monitors the solar illumination that helps for some of the post-processing steps. We have a reflectance standard tarp that you see there folded up in the background, also used to help back out to units of reflectance or reflectivity. And then, of course, not shown is all the software that we sell with this kit that's used to collect and post-process the software. And I'll be showing some of that post-processing today. Just a quick introduction to the radiometry of remote sensing, and specifically remote sensing with a hyperspectral imager, although these concepts apply to other instruments as well. First, we have the downwelling irradiance from the sun. And obviously the sun is not an ideal source of light, since its intensity and spectral profile changes with cloud cover and aerosol content to the air. That light then bounces off of the ground and is collected by the airborne instrument. And that is, in this case, called the at-sensor radiance, or just radiance usually. And then you see on the ground, I have a little cartoon of a reference tarp. And ideally, you can take the downwelling irradiance and the at-sensor radiance and compute the reflectance of the object on the ground, assuming certain properties of that material. Most importantly, that material is Lambertian, or that it scatters light equally in all directions. The reference tarp in that process is only so good. So the reference tarp helps us correct in a little bit more accurate way to reflectance on the ground. Sometimes the tarps aren't convenient. In that case, you want to use a downwelling irradiance sensor. Sometimes you want the accuracy of that the tarp provides. So a few applications of airborne hyperspectral, and this is shown approximately in distribution of our customers, that is how many instruments we sell for these particular applications. So agriculture is our biggest application. A hyperspectral imager can detect plant stress very early, things like drought or lack of nitrogen or other nutrients in the soil. Those types of things can be detected much earlier with a hyperspectral imager, allowing the farmer to correct the problem, either adding water or fertilizer. So within agriculture, plant health is a very common application of this. You can do weed identification which is also useful for farmers to locate the weeds in their fields, or outside of agriculture if you're looking at invasive species within a forest or riverbed. This is another application. So both of those kind of get bundled together in the ecology segment, where you're looking at the health of a forest or stream bed, like I said, looking at different species, looking at the overall health of that environment. We have a few customers looking at algal bloom tracking in waterways. So as the summer goes on and the water gets warmer, it's very common to have an algae bloom within a lake. And if that lake is a water source for a metropolitan area, that can cause problems. So it's good to find that algae early and track it before it enters the intake to the water distribution centers. Similarly, you can look at groundwater pollution, where if you can monitor the health of certain plants above the ground, you can look at pollution underneath the ground. We have some customers doing that. Anomaly detection is another field that we've been involved in, where you don't know what you're looking for, but you know that you're looking for something that is statistically out of place in the environment. And then finally, we have mineral identification, which usually happens in the near infrared or shortwave infrared. Not very often is a visible near infrared instrument used, and Resinon offers both of those systems, or all three, I should say: visible near infrared, and shortwave infrared. Here's a screen capture of our analysis and post-processing software called Spectranon. It will allow you to do almost everything you need to do with your airborne data, from converting the data to proper units, or georectifying it, and then doing the analysis or classification of that data as well. And so now I will show you a short demonstration of post-processing airborne data with Spectranon. So here I have Airborne Data Cube, and this is a farm just outside of our office here. And I like this cube because you can see a couple of wiggles. These should be straight rows of plants and crops, but you can see a few wiggles in there that we will georectify, straighten those out, and also place them on the ground. You can also see there's lots of different species in this plant. This is a small farm. You can see some pumpkins on the ground if you look carefully. And if I grab this tool, I can see the reflectance spectrum underneath the cursor. But this data is still raw data. So the first step typically is to convert it to units that you want to work in. And right now we'll correct it to units of radiance, in which case I choose the calibration pack that comes with the instrument from the factory. And now we have a data cube that is in units of radiance. If you remember our diagram there, the at sensor radiance. So we're not in reflectance, and we're not going to go to reflectance right now. A lot of times radiance is very useful in its own right. It really depends on your application. So we'll do a quick species identification on this, and I have a sort of pre-collected spectrum of kale. I know that Germany grows a lot of kale for export, mostly to the US. We like to eat lots of kale here. And so now I am going to, actually, sorry, let me back up and do a georectification first. So in this case, I don't have a digital elevation map for this cube, but you can use digital elevation maps if you have one. In this case, we know the field's pretty flat and we know the elevation. So I'm going to enter in the elevation of this field on the ground and the field of view of the lens that was used to collect the data. And this will churn just a little bit. And what this is doing is it's taking both the GPS information and the attitude of the aircraft collected by the inertial measurement unit to project these pixels back onto the ground, both to rectify the image and also to assign a GPS location for each pixel. So now you can see here that the wiggles have been straightened out. Those wiggles were caused by either the aircraft turning hard or some turbulence. This was taken on a multi-rotor UAV system. So now let's go back, and we're going to use an algorithm called spectral angle map, which is a very simple algorithm. And we're going to try to detect all the kale. And one drawback of spectral angle mapping is that you need to enter a threshold typically. And so now we threshold it down to see that we can find a few rows of kale. This result could be improved upon greatly by using a more sophisticated algorithm, such as logistic regression or either random forest. And you can see within Spectranon here, we have lots of different classification algorithms. We have lots of different analysis tools, utilities, anomaly detection, lots of agricultural algorithms as well. And this software is easily extended if you have an application that you need an algorithm for. Either we can help you write that, we can write that, or you can venture off on your own. Everything's written in Python, and it's fairly easy to extend Spectranon to different application areas. Let's go back to this cube. I'll do one more real simple analysis here in the agricultural sector. The classic algorithm is the normalized difference vegetation index. It's not the most powerful by any means. There's much more sophisticated algorithms available these days, but we'll use it here. It's a very quick way to visualize the health of these plants. I'm going to add a little color to the display, and I'm going to just move the contrast down a little bit to help show what's happening. So in this case, the more yellow pixels, the healthier their plants are. The bluer pixels are going to either be not plants or unhealthy plants. So here's a quick way to visualize maybe where you need some water, need some fertilizer. And then finally, I'm just going to export this to a Google Earth file. And there you go. You have a very quick map of the health of this this farm and that field. And of course, if this were real data, you'd have a mosaic or a little bit more complete map. But in this case, just a single data cube to demonstrate with. So that's what I have to show you. I thanks for your attention and your time, and I'll hand it back over to Martin now.
Yeah, thanks again to Adam Stern and Casey Smith, especially for getting up so early for them. It was pretty early when we started coordinating before, and yeah. So now we have the first question. Yes, what are the data formats from the Airborne system? So the data formats are binary files. They are not really encoded. So one is a header file and the other one is the data file that yes, that will give you the data also human readable.
And just to elaborate on that, our data is NV standard format, so you can open our data with NV or MIPS or any other software that uses hyperspectral data or can open hyperspectral data. Our data should be compatible with it.
So next one. Yeah. So maybe Casey again, what kind of aircraft can the system be used on?
Sure. Our system has been used on many different types. Most commonly these days, it's on multi-rotor UAVs, but we have flown on fixed-wing airplanes, on helicopters, on we've even done some powered gliders in the past, and blimps. Any system, because our system is sort of turnkey and standalone, we don't rely on any infrastructure on the aircraft necessarily. We just need a power supply and to hang the antenna somewhere, and it can be flown.
Okay, thank you for that one. So yeah, so what's the typical ground resolution of the airborne system? Maybe we can talk a little bit about spectral resolution as well, as I've seen the question sometimes in the question chat.
Sure. The ground resolution is really a function of two things. One is how slow you can fly your aircraft versus how many frames per second you are collecting. So the frame rate of the system. Yeah. Most of the rotorcraft can fly quite slow, down to a few meters per second, and our system can collect up to 250 frames per second for the visible and near infrared system, if there's enough light available. Typically, you're bound to a little slower frame rate than that, just to because we don't have the light available from the sun. But you can get down to several centimeter resolution in the long track. The cross track resolution is dependent on your altitude and the field of view of the system. So typically you want to try to match your cross track resolution with your long track resolution. And to clarify, the long track resolution is the resolution in the direction of the flight, and the cross track resolution is the resolution orthogonal to the direction of flight. And to match those two resolutions, we have a software tool that's included with the system that you enter in the various parameters you know, commonly your altitude of your system and the ground speed of the system, and then it helps you compute the rest of the parameters to set up the data collection software so that you can achieve the resolution that you're looking for. So the answer is it depends quite a bit, but we have customers that are trying to resolve individual leaves on plants, and then we have customers that are flying 10 or 15,000 feet. Sorry to use feet, 3 to 5,000 meters to collect very wide areas, such as our algae mapping projects, where they're looking at very big lakes where they want to fly high and cover a large area.
Yeah, so I think, the spectral resolution typically depends on the type of camera you choose, especially when you have, especially when you go between visible and near infrared. Typically, near infrared imagers have a bit lower spectral resolution, and the visible ones have a a spectral resolution starting from, I think, 1.3 or 1.5 nanometers, and with the Pika XC2, and the Pika L should be around 2.5, is it 2.5 nanometers, right?
Yeah, that's about right.
Yep. Okay. So yeah, come on. Whoops, that was too far. Okay, I had some other, but they didn't seem to be connected at this time. Yeah. So I have the I don't have the latest questions written down, but I have some of that here because the audience is very active. So there was a question, I think this is going to Adam maybe. What material is that reference tarp made of?
Yeah. So the reference tarps are made by our friends out in the Western United States, a company called Group 8 Technologies, and I'm not exactly certain the materials. Casey could answer this best. He's our lead engineer, chief engineer on these Airborne products. But just briefly, those reference tarps have a roughly constant reflectance as a function of wavelength. Casey, do you have more details on the materials of these tarps?
Yeah, it's a cloth tarp, obviously, but then it's coated with a proprietary material. So I don't know much about that material, but it's similar to Spectralon or Fluorolon in that it's intended to be spectrally flat. They do measure the absolute reflectance of that material in batches at the factory, and we can provide that so that you don't have to assume that it's spectrally flat. You know exactly what that reflectance of that tarp is. And we sell different reflectivities to help match what you're looking for. Typically, a 12 or 15% tarp is a good starting spot.
Great, thank you. So another question was when you talked about plant nutrition, do you know the percentage of water via one big data pool, or do you need to train the software for every field separately?
Yeah, forgive me, I'm not a plant scientist, but from my interaction with the plant scientists that buy our systems, I think typically it's fairly species dependent. So you can look at a species and sort of know the stress to that plant based on its reflectance. But that species to species, you have to account for those differently. So you don't have to train each geographic location differently, but you do have to treat each species a little bit differently. I hope that answers that question.
Yes, I think it's necessary to train a little bit or to do kind of a calibration curve, and then you should be able to determine let's say drying stress or something via the reflectance data. So let's see. Another question is there a hyperspectral radiometer available? So I think this points out to the downwelling sensor that's available with your systems optionally.
Yeah, that could mean a couple of different things, actually. Sometimes it refers to a spectroradiometer is usually a single point spectrometer that's been calibrated to absolute units of radiance or irradiance. So in that case, absolutely. Our airborne systems are all calibrated at the factory into radiometric units. But perhaps that question could also mean the downwelling irradiance sensor, which we also calibrate and sell as an option with our airborne systems. And that system can either be flown on the aircraft or it can be used on the ground.
Yeah, I think it's the first point you answered. I think this is yeah, when you have a radiometric calibration on that hyperspectral camera, then you can use it as a hyperspectral radiometer device, some kind of that. So I don't really know. I give this question just as I have it here. So, is there a preferred GPS from the base station or course data, correction data for auto rectification?
Yeah, I can answer that. So right now we use products from SPG, and we specifically use the Ellipse N. And at the moment, we're not using ground station or base station data to help correct for the drifts, the atmospheric drifts of GPS. But there's an exciting development happening this fall, hopefully in the next month or two. SPG is releasing a new version of that unit that can use a base station for RTK or real-time kinematics, which will really increase the accuracy of our data. The details of that base station, as far as I know, like I said, this is an upcoming development for us. I think any base station can be used that outputs the standard formats. So I think the system will be pretty flexible on what base stations can be used. And also to clarify that, you don't need to use a base station if you don't have one. It just helps increase the accuracy of the GPS data.
Okay. So what kind of methods do you use for data reduction? Do you use all wavelengths for classification, or do you select significant ones? If you do, what methods do you use to select most significant features?
Yeah, that's a good question. The system, the data as it's collected, the only way to reduce the data size is to use binning or averaging of adjacent spectral channels. So that's a setting in the data acquisition software. And the trade-off there is you lose some spectral resolution, but your data is smaller. Once you have the data collected and you want to do some data reduction or feature selection, then lots of algorithms will do that on their own. Most of the machine learning algorithms will discard spectral bands that do not contribute to the accuracy of the classification or do not contain information, is another way to think about it. But then there's also lots of other techniques, univariate feature selection or recursive feature selection. The exciting thing right now is that machine learning has gotten mature enough and fast enough that all of these algorithms are available for us to use in Spectranon and really fit with hyperspectral data pretty well. So it's a good time for hyperspectral data analysis, I think.
Great. This is a little bit more special question, but I think I know the answer. So how deep can the groundwater be in order to track it? Also, what types of minerals can be identified and what is their minimum concentration in order to be identified with airborne systems? So let me start off a little bit. I think the groundwater, when you go for soil classification or something, to track groundwater, you need some kind of surface, some surface artifacts so you can see where the groundwater is. So the soil needs to be a little bit moist or something. Correct me if I'm wrong, Adam or Casey. So for this question, the minerals and minimum concentration depends, I think, on illumination, on the type of reflection they have, so the amount of absorption and reflection. Yeah.
The studies that I've am aware of for the groundwater, you're sort of vicariously tracking the groundwater pollution by looking at the health of the plant on the surface. So in that case, the groundwater has to be close enough to the surface that the plants are absorbing it and using it, and the concentration has to be such that it will impact the health of that plant. So I don't think that there's any way to give you an absolute depth of that water other than that the plant has to be affected by it. In terms of the mineral concentration, that's also a matter of the contrast of the mineral to the surrounding areas. So if you have a mineral that has a really unique spectral profile, that can be detected in lower concentrations than minerals that have sort of a bland or similar spectral profile as other materials or minerals. In that case, you'd need much more concentrated deposits. So sorry, it's really hard to give absolute numbers like that. It's all very application specific.
So this one is more a little bit general. So what is the positioning error of your georeferenced auto-rectified image collected with your standard GPS IMU? And how can you improve the precision of auto-rectification?
Yeah, that's a good question. At the moment, we are limited to usually the GPS error is the most significant error present. And at the moment, that error is about 3 meters under very good conditions. Sometimes it can be down to 1 meter. So the easiest way to improve that is to wait another couple of months until SPG releases their new ellipse-N. Other than that, the GPS error is a really hard problem. So using a base station will get us down to sort of centimeter type errors for GPS. And then of course you still have the error from the inertial measurement unit, which will be I think 0.2 degrees. So there's some of that error that will still be present. And it's really a matter of how accurate you need it to be. You can Spectranon. One thing that Spectranon doesn't do is do ground point control or ground control point rectification, but our data can be imported into ENVI, and ENVI has the ability to use ground control points to sort of rewarp your data to known locations on the ground, at which point you can bypass a lot of those errors as well, as long as you have known points on the ground.
Okay, thank you for that one. And I think one last question there's time for. I don't know if it's directed to the Airborne system or the camera itself. But the question is, can it be mounted on a pan tilt unit? So I think let me go to the camera. When you have when we go a little bit away from the Airborne system, when we go to the outdoor field system that has been shown, that is basically a tripod with and a rotation stage. Yeah, then you will have the chance to have a pan or tilt unit, because with the rotary stage you can scan the area in a horizontal or vertical way for hyperspectral imaging. If there's when it comes to the Airborne system, I don't know, Adam or Casey, the cameras are mounted on a gimbal, as far as I know. And is there a chance to I think this aims to yeah, tilting the camera in flight or something?
Right. Typically, the systems are mounted on a gimbal, but the purpose of the gimbal is not to pan it or tilt it, but rather to keep it pointed straight down, keep it pointed nadir during flight as the aircraft tilts with flight or gets blown around by the wind. It helps keep the flight lines straight. So it's pretty useful to use a gimbal for that reason. It doesn't have to be. If you're trying to eliminate some of the weight that the gimbal represents or the complexity, you can also hard mount the system directly to the airframe, but a gimbal is nice.
Okay, thank you, Adam and Casey, for answering the audience's questions. And yeah, there was a thanks in the question section. So I think we answered some questions that were given to us. And if there are more, please feel free to yes, to contact me via email, and we will I will go and follow up to your questions and clarify together with Adam and Casey to give you the right answers to your questions. So last but not least, thanks again to Adam and Casey for getting up so early and giving this great webcast to us and their presentations. And before we are closing, just let me invite you to our next webcast, which is dated on October 7th, 2020, which will be a machine vision imaging with very high definition SWIR cameras. Yeah. So this will be held on October 7th at 3 p.m. Central European Time, and for all people who want to rewatch this presentation, the on-demand version of our webcast will be available on the Laser 2000 website under the section News or Aktuelles in German. Under the section webcasts. So it should be available next week mid next week or Thursday, something like that. So thank you for joining and for watching us, and all the best wishes to everyone who supported us, and stay healthy, everyone. Goodbye.